requires elimination. Okay, so what we are going to talk about today is elimination reactions. And in the case of elimination reactions, what ends up happening is the base here. So what actually goes on in an elimination reaction is we form an alkene. And the reason why elimination reactions basically go hand in hand with substitution reactions is because the components are essentially the same or very similar. So you've got an alkyl halide, you have a Lewis base, and in this case, so the similarity is with the substitution reaction, it's a nucleophile, Lewis base, which happens to be a nucleophile. In the case of elimination reactions, it's a Lewis base, but it's actually a Bronsted. It's actually a Bronsted base because it's going to be grabbing a proton. So it's the conjugate acid of this it's protonated. And you still have your leaving group, which has departed with the electron. So the basic components are all the same. Now, the key point is that in an elimination reaction, protons are going to be removed from the carbon next to the leaving group. So often if there's a mistake in this type of, so you're going to be removing one of those two protons to make the double bond. Often if there's a mistake, sometimes people try to remove protons on the same carbon as the leaving group, but nothing happens. Nothing happens to the two protons in green. The base is going to remove the protons which have been circled. So that's the difference between a substitution reaction. So a substitution reaction, the Lewis base is going to attack the carbon with the leaving group. An elimination reaction is going to attack the protons next to the carbon with the leaving group. And there will be two mechanisms to this reaction. The E2 and the E1. And so these are very similar to the SN2 and the SN1. So the rate in an E2 is some rate constant times by the alkyl halide and the concentration of the base, whereas the rate in an E1 is only dependent upon the concentration of the alkyl halide. And so the E2 is a bimolecular reaction, so it's bimolecular. It requires the two substrates to hit each other, and E1 is unimolecular. So the rate determining step involves only one of the two. So E1s are going to form carbocations, just like an SN1. So because it forms carbocations in the rate determining step, if we had three different types of alkyl halides, which one would an E1 elimination reaction take place the fastest with? Tertiary, secondary, or primary? Based upon what you know from SN1. Tertiary, right. So it's really for this there's a big check mark for E1s can take place for tertiary, there'd be a smaller check mark because this would be slower for secondary, and it would be a big X for primary. Now, practically, trying to do an E1 elimination on a secondary, it becomes unpractical in all honesty. This I'll just put here, becomes impractical. I have to check my English, if that's impractical. Yeah, I think that's the correct word. It becomes impractical because it was the ones in pink. So let's do a mechanism for an E1, and then we'll do a mechanism for E2. And we're going to see how this works. Okay, so here we've got a tertiary alkyl halide. Okay, so the first step, actually, let's make this easier for a second here. Okay, so here is tert-butyl bromide. So the rate determining step is going to be that the leaving group leaves with its electrons, rate determining step. And we are going to form a carbocation. So here's our carbon. This is technically coming towards us, and that's technically going away. So we form our carbocation, and our leaving group is left with its electrons. If the bromide just comes back and attacks the carbocation, we're just going backwards, right? So that's not important. Then the next step is that, so tertiary carbocations, remember tertiary carbocations are more stable than say primary. And one of the reasons is because of hyperconjugation. So there will be 3 protons which have basically lined up the electron density between 3 of the carbon-hydrogen bonds will be parallel to this carbocation. So it can hyperconjugate. And in this situation, all which happens is the base comes along, and it removes one of these protons, and then this goes in to form the pi bond. So we get we'll make our alkene. So this would then become a p orbital, CH3, CH3. And then electrons are being shared in the p orbitals, so you've got your alkene. So in this reaction here, it doesn't matter which of the 3 protons gets removed. They're all the same. It all produces the same product, which is this, if we're looking at it from above. So in each case, so if this is carbon, let's just draw put a little star here in green. If this is the carbon with the leaving group, here's the carbon with the leaving group, here's the carbon with the leaving group, here's the carbon with the leaving group. So it's going to be a carbon which the protons from one of the carbons next door, that in this case, it's one of these protons here that which gets removed. So when we're making an alkene, it's the proton next door on the carbon next door which gets removed. So I removed the one in yellow, but I could have also removed like this one in green over here, or this one in blue over here. They all could have been removed, but in this case, only one of them was. And they all produce the same alkene. They all produce the one which we've drawn down here. So in an E1 elimination, you form your carbocation, then the base removes one of the protons, and then you form your alkene. So the energy diagram for this is essentially identical to that of a SN1 reaction. So free energy, reaction coordinate. Got some alkene, determining step, a bit higher. Starting material. So here would be our carbocation. And we would have two transition states. But the rate determining step is going to be this first one. So this will be delta G dagger. And that will be the rate, this will be the rate determining step. So the rate determining step is the bromide leaving right here. This second step would be very quick. And so actually, when it comes to the first step of this transition state, the formation of this carbocation here, this is exactly the same for an SN1 reaction. So there's another pathway, and depending upon what other reagents you have in what your reagents are, there will be another pathway which could be slightly higher in energy or could be slightly lower in energy that would give you the SN1 product. So so often E1 eliminations take place and some of the side product will be SN1 products, or sometimes the SN1 product will be the major product and the E1 product would be a side product in that reaction. So they really go hand in hand because the very first step is exactly the same. They would both form exactly the same carbocation. And it just depends upon what you've got, what your solvent is, what your Lewis base is. Is it better nucleophile than a base, or is it a better base than a nucleophile? And that would influence the ratio. Now, one of the things that's, if there was a choice between protons to be removed, so let's change this slightly. Let's say that our okay, so here we go. So all I've done is I've added we now have, instead of 3 methyl groups, we have an ethyl group and 2 methyl groups. So, and let's say that our conditions are, this is run in water, and we are using very dilute hydroxide. So very dilute hydroxide is gonna be it's gonna behave more like a base than a nucleophile. So, but it's dilute. So that's the key point. Whenever you see very dilute, this basically hints that this is an E. We're trying to do an E1. Okay, so the first step will be that the leaving group leaves. So There we go. And we will form, so this will be, let's go here. We form our excuse me. Ouch. Let's see here. CH3. So I've drawn a carbocation here, and I've drawn it in a way so that there'd be the 3 hydrogens are all hyperconjugating to that positive charge. Now it turns out that there's 2 potential pathways here. I'll draw one in pink and I'll draw one in blue. Ouch. Excuse me. So if you remove either of the protons here in pink, so if the base comes along and grabs these, and then so these electrons will move there, we are going to form the following we'll make the following alkene. It'll be carbon, H2, CH3, CH3. We'll make this one. So it'll be the ethyl and the methyl. So here's your ethyl group on, this is the ethyl over here, and then your methyl. You'd make this alkene. If you were to remove the proton in blue here, so your base comes along and grabs this, then the alkene we make is as follows. Methyl, CH3, CH, C, CH3, CH3. So the carbon with the positive charge, this carbon here is here, and it's here. And so you actually make 2 different constitutional isomers of the alkene are possible. And it turns out that, alkenes, their stability the more R groups on the double bond, the more stable they are. So alkenes, they want more R groups. So in this case, on the bottom over here, this one's got 3. 1, 2, 3. This one over here is only got 2. 1, 2. So the product from the elimination of that blue proton, this is the more stable product. And we're thinking thermodynamically more stable product, whereas the one over here on the right is less stable. So with E1 eliminations, they tend to favor the more stable one. So this would be the major product down here on the right. Now there's a method to make this one on the right over here. There's a way to make this one in yellow. And we'll talk about that a bit more when we're doing the E2 elimination. So there's 2 different alkenes that could be possible if the molecule is not symmetric. And with E1 eliminations, you tend to favor the most stable product. You get a mixture of them, but it'll be the one which is the majority of Chemists don't like making mixtures of things because it's more work. You have to separate them, right? So we tend to like to do the least amount of work possible. That's probably something common in human nature. And so you want to develop a reaction scheme that's it's going to give you what you want in a high yield and with the minimal number of side products. So that's typically what you want to do. And so when I was talking at the very start about how for E1 eliminations that for secondary alkyl halides, this is really slow and becomes impractical. That's because we can use an E2 elimination reaction and it'll be faster, it'll take less time, and it will probably be more selective. So for what we do in this course, the main type of reaction where we're going to see in E1 is pretty much exclusively with tertiary alkyl halides. It's going to make everyone's life a little bit simpler. Because for these types of reactions, really there's a couple possible products here. Like in this last one, if you use something which had some, like there's also the other potential product that you could have the hydroxide attacking the carbocation for the SN1 reaction too, right? So there's a whole host of possible side reactions with this. So that's why it's not very practical in many ways. So, but it's something we typically have to talk about. Now, any questions on this at all? Not yet? Okay, that's all good then. Let's do the E2, because this one is far more useful, and you've got a bit more control over what's going on. So in an E2 elimination reaction, I'm going to draw this like this. So in an SN2 reaction, the neat thing about the SN2 was that the nucleophile had to attack the carbon on the opposite side of the leaving group. And it did that because the sigma star orbital of the bond which is being broken, this carbon X bond, the sigma star was right on the opposite side. So something similar takes place here. So the sigma star of that sigma star of this carbon X bond is here. And if you want to break this bond, you need to put electron density into that orbital. And so it's going to be these electrons here that are going to do that. So they're going to get donated into there to make the pi bond. You're going to break that bond and it's going to convert into a pi bond. And so there's a geometry which is required for this type of reaction to take place. So your base, let's call this B, it's going to attack the proton. Those electrons are going to go into the sigma star, and then the leaving group is going to leave. If we draw this, I've drawn this from a sideways view, and it might be easy, it might be hard to see what's going on, but if we draw a Newman projection of this, we are going to see that, is our eyeball, that the H and the X have to be anti. They have to be anti to one another if we draw a Newman projection. They have to be lined up because when you make your p orbitals of the alkene, they have to be lined up. They have to be parallel to one another. So if we are to draw this, this is our eyeball, the first carbon, the X is right below us, so it's down. Then on our right-hand side, going into the board, because it will be the R2. And on our left-hand side will be R1. And right above us on the back carbon is the H. And then the R4 and R3. So the H and the X are anti. They're perfectly lined up. So these two guys are anti. So this is the lowest conformation in which the elimination can take. This is the low energy conformation. So if this is to take place, we're going to generate a double bond in which, I'm going to erase this little anti bit here for a second. These two groups are going to be on the same side. And these two groups are going to be on the same side. So when we make our double bond, when this gets eliminated, R2 and R4 will be cis to one another, and then R1 and R3 will be, so they're on the same side. So now there's actually another high energy conformation which this elimination can take place on, and that's if everything is eclipsing. And if we wanted to do that, we would need to rotate this X all the way up so it is eclipsing the H. So let's draw that over here for a second. X. So if I rotate this X to the H, that means the R2 is going to get rotated down over here. R2 and R1, H. And now the two are lined up because they need to be lined up because those two sigma bonds are going to be converted into p orbitals to make the double bond. And in this case here, the double bonds, now the geometry is going to be it's going to be opposite, right? Now the R1 and the R4 are on the same side, and the R2 and the R3 are on the same side because you had to do this rotation. So so this high energy, this is high energy. It's less likely to occur. So it's the E2 elimination. There's this requirement that the proton you remove has to be anti to the X. So it limits the choices of the protons that are available. Sometimes if there's only one proton available and you can't make this conformation, then an E2 elimination can't take place. I guess the place we would see this the most would be with regard to chairs. So for example, let's say that we have let's say that this is our two-dimensional structure of this tri-substituted cyclohexane. We're going to put all these substituents on here like we would normally. Let's see here. So methyl group up. So in this conformation, methyl group up, bromine down, Br. Carbon 3 methyl group down. Down would be over here. So this would be axial. This would be axial. This one would be equatorial. And there would be a conformational, another conformation that would exist. 1, 2, 3. So remember, ring flips doesn't change if it's up or down. It changes if it's axial or equatorial. So on carbon 1, it's still up, methyl group. Bromine is down, bromine, and methyl group down. B. So if we've got these two chairs, equatorial, axial, which of the two is more stable, A or B? A whole bunch of people are saying B, and it's B because? Right, there is least number of axial groups, and remember, axial groups have got those 1,3 diaxial interactions, which are destabilizing. Excellent, okay. So now what's interesting is that in chair conformations, leaving groups to eliminate, they must be axial. Equatorial, the equatorial, when a compound has is in the equatorial conformation, the proton, it's impossible for the proton to be anti to it. So now I tried to draw this sort of, so if you draw a Newman projection of chairs, the equatorial substituents are here, equatorial. And you'll notice that it's a carbon bond. There's a carbon atom up here, which is anti to it. But if you're an axial substituent, then the proton can be anti to it way down over here, right? So in these two chair conformations, only one can the elimination reaction take place, and that's in conformation A, because only in conformation A is the bromine actually axial. And the other thing which is interesting about this is that you'll notice that, so remember, it's the carbons next door from which the proton gets removed. And the proton itself has to be axial. So in this case here, you'll notice that on carbon 3, there's a proton which can be removed. But on carbon 1, the group that's there is a methyl group. And it can't be removed. It has to be a proton. So there's only one possible way that this substrate, there's only one possible proton which can be removed, and it would be this one in purple. So when the base came in and attacked, base, grab that, these electrons go here, and this disappears. And so there's only one possible product, and that product is, we'll erase this for a second. So we've removed the proton from carbon 3. So 1, 2, 3. This methyl group is still up. There's a double bond between 2 and 3, and the methyl group is on carbon 3. And I've drawn carbon 3. This methyl group is a straight line because the carbon-3 is now sp2 hybridized, so it's flat, trigonal planar, so there's no stereochemistry here. So there's only one possible product for this case, and that's the one which we've drawn here, because only this proton in orange can be removed. And it's in the least stable chair conformation. So this reaction would be a little bit slow because you'd have to ring flip into the least stable conformation and then it would get eliminated. So let's see, what would be a good yeah, let's do another example here. So let's pretend that we have this. And
my boom.
sorry. Let me see here. It's kind of funny. Okay, so let's put this here. My example was actually going to be too complicated from what I was thinking. So I'll move on from that. So with cyclohexanes, these questions are actually quite good because it gets everybody to draw their cyclohexanes again and then choosing the correct proton to be eliminated. So that's one interesting point to cyclohexane. So for an E2 elimination, the proton has to be anti to the leaving group. And if it's in a chair, then the two substituents have to be axial. And they'll be axial on opposite ends. Like one will be above the ring, one will be below the ring. So let's see here. Energy diagram. I guess we should do that. Free energy. So the energy diagram very much resembles an SN2 energy diagram. There's just one peak at the top. There's no intermediates. And the transition state would look something like this. You are breaking you're making a base proton bond, you're breaking the carbon proton bond, you're making a carbon-carbon double bond, and you're breaking the carbon leaving group bond. So it would look something like that. That's basically what it would look like. And so this structure would be the thing at the top of this peak here. So it's got less moving parts. Well, actually, it's got more moving parts than the SN2 than the E1, but the energy diagram is far easier. So that's what this would look like. So E2 energy diagrams look like SN2 energy diagrams, and E1 energy diagrams look like SN1 energy diagrams. So it's history repeating itself in that sense. So that's nice. Okay, now let's look at So remember with SN2 reactions, they worked super well with primary. and they were not so bad with secondary, and they couldn't work at all with tertiary. Now, the big difference between E2 is that E2 elimination reactions can happen very well under all of these conditions. So out of all of the 4 types of mechanisms, E2s can happen for any type of substrate. So E2 is the one which we could see a lot of. The and because the reactions tend to be faster, that makes them more practical than an E1 in many cases. So E2 is an E2 elimination is quite a useful reaction in that sense. So there are 2. Let's look at some regiochemistry here. So let's say that we have a secondary alkyl halide like this. If we do an elimination reaction in E2, there's 2 possible products that you can form. You can remove one of the protons from this carbon here to give a double bond here, so the least substituted. Or you could remove one of the 2 protons from, say, this carbon, and you would make a double bond that is more substituted. So one of these is technically a kinetic product. One of them is a thermodynamic product. So this one would be the kinetic, and this one would be the thermodynamic. Question. Why is it called more or less substituted? Okay, so with alkenes, if it's bonded to a proton, that's not a substituent. But if you start adding like R groups, any R group, we would call that a substituent. So when you've got a substituent attached to something, it's like so substituted is just saying the number of alkenes attached to it. It's a fancy word for that, I guess. So more R groups, actually it's anything but a proton, really. For what we're always doing, they're all going to be carbon atoms, but if you had a nitrogen or something like that, we would even call that a substituted product. So, but for the most case, it's just the greater the number of R groups. So in this case here, you've got 1, 2 R groups, and over here we've only got 1. So does that make sense? It's sort of very similar to what we had before when I was doing where were we? The more stable, this alkene stability, the more stable product is the more substituted product. I was just using different terminology. Okay, so when elimination reactions were being discovered, it was a Russian chemist which basically discovered this. And the reactions that he was doing were forming the most substituted product. And so these have been basically called, you get to discover something. If you're lucky, you get your name associated with it. So these more substituted thermodynamic products would be called Zetsiev's products. And then another chemist developed a way to make the kinetic product using different conditions, and that was Hoffman. So sometimes the least substituted product are called Hoffman. I think there's 2 N's there. And the more substituted product is called Zetsiev's. So if you ever hear that terminology, that's what this means. So, right, Now, what conditions do we want to use to make these two products? So for Hoffman's products, what he did was he used bulky bases. And Zetyev's is basically using small bases. So what's big and what's small? And these reactions, E2 elimination reactions, to get to, or I guess we'll get to this in a second. So bulky bases are what we'd use for Hoffman's products, and small bases would be used for Zetyev. So what's a bulky base? Bulky. Something which has steric hindrance. Something which is sterically bulky. And the one which we will use the most is tert butoxide. So tert butyl group, oxygen. The most popular one is the potassium. With potassium is the counter ion, but we're not really worried about the counter ion at all. So tert butoxide is the simplest one to use. You can take tert butanol and just throw a little chunk of potassium in it, and boom, you're going to get, after it ignites and has a little fire show, you're going to make tert butoxide. So that's one. Tert butyl lithium is another one. This is a bulky base, except for it's a carbon bonded to lithium. So this is one of the most, this is the most basic base there is. And it's so reactive, you need to use an aprotic solvent. So usually you use this in THF or ether. Those are two. Another one would be these guys here. The ring size can vary, so I'm just going to draw little loops. These are DBU and DBN, and these are nitrogen-based bulky bases. But tert butoxide is probably the one we'll see the most. And when you're using tert butoxide, the solvent you would use with it would be tert butanol. With tert butyl lithium, it would be THF or ether. And oh yeah, there's LDA too. This is another one, which is LDA. This is a nitrogen-based, nitrogen with a minus charge, so it would be run in THF and ether as well, because both of these would react with a protic solvent. They would just deprotonate the solvent. So you need to use an aprotic solvent, THF or ether. But these are the big bulky bases that we'd use. For a small base, like methoxide, ethoxide, hydroxide, I guess. These are all good small bases. And the solvent you would use for each one of these is the corresponding alcohol. So methanol or ethanol. With hydroxide, water. A lot of organic substrates aren't soluble in water, so sometimes you'd use something else to help solubilize that. But that's why hydroxide isn't used as much, because this can complicate things a bit. But anyway, so what we'll use the most is methoxide or ethoxide. So these would be small bases. Now, the reason why this is the Hoffman product uses bulky bases is that when that large base is grabbing a proton, it's easier to grab protons on the exterior here than it would be for a big bulky base to come in and grab a proton which is in the middle. So that's why bulky bases grab one of the protons on the edge. And this thing would have to spin. So let's draw like a Newman projection. Yeah, let's draw a Newman projection. So let's say that this is our compound. And actually, I've drawn an eclipsing conformation here. I don't want that. Okay, so let's draw this Newman projection. So the N carbon has only got protons on it. That's nice. This group going down here, this is a 1, 2, 3. This is a propyl group, propyl. On our left-hand side, if this is your eyelash, this will be the bromine, bromine. And here's the H. And so your bulky base would just have to come along and grab this proton here, because this proton is the one which is anti to the leaving group. Now let's draw the same thing here. Let's draw another Newman projection looking at this down this bond here, and try to bring our big bulky base in there to attack that. See if we can do this correctly. Going up is an ethyl group. And we've got our 2 protons. And then we've got, on our right-hand side will be the bromine. Down will be a methyl group. We've got an H over here. So this, yeah. And then now, if you want to bring your big group in, you've got to worry about, so this is the proton here, which has to be removed. And now we've got like a methyl group over here and an ethyl group over here. So if it tries to come from up here, it's blocking this ethyl group's getting in the way, and then you've got the methyl group getting in the way. So it destabilizes that transition state because there's too many large groups around it to get in the way, in particular the ethyl group. So it's easier to remove protons on the outside over here with big bases, and it's less of a problem to form to remove the interior protons with small bases. So that's basically the way that E2 eliminations work. You if you use a small base, and the bases that we'll be using will be methoxide, ethoxide, hydroxide. These will form Zetsiev's products. And if you use large bases, these will form the Hoffman. Now, in the case of primary alkyl halides, there's only one possible product, right? So X, it doesn't matter if you use tert butoxide or methoxide, because there's only one carbon which actually has protons on it. So you're always going to get the same answer. Okay. Now the hard part to all of this is how do I know when I've got a base and how do I know when I've got a nucleophile? And so I guess I should stop and ask, are there any questions so far? No? Okay, well then I guess the next question will be, how do I know when I've got a nucleophile? How do I know when I've got a base? Let me see if I can dig that up. So yesterday I would have sent out a PDF file of a decision matrix. Of course. Okay, so here's basically, can everyone see this? Yes, okay. So I sent this out at the end of class, sorry, just to basically give everybody a way of analyzing everything, because this is really, it comes down to analysis here. So there are certain Lewis bases that can only behave as nucleophiles, at least for what we're doing in this class. And these Lewis bases are things which we would have seen before that are polarizable, low on the periodic table, or so sulfur, iodide, bromide, chloride, or guys that are nice and linear, like the cyano group or the let me see if I can draw. These types of things. So the cyano group or the azide, like these are one of the good things which makes these things good nucleophiles is that they're linear. So that would be things that are only nucleophiles. So if it's only a nucleophile, this means it's only going to do an SN2 or an SN1. That's things that are only bases. This means that these are going to do only E2. And why not E1? Because they're such strong bases that they're basically it's just going to be E2. So that's helpful. Then there's a series of compounds that could be Lewis bases that could be both, right? So hydroxide, ethoxide, and methoxide. These are relatively strong bases. They're oxygen-based bases. But practically, when we use them, they're often used in the solvent, the corresponding conjugate acid. And so these are mainly going to be E2 type, follow E2 type situations. Where things that are better nucleophiles and bases, these will be involved in substitution reactions. And then there's some very weak ones. So these are going to be involved in either E1 or SN1. So the very weak nucleophiles and bases, it mainly be SN1. So these are basically the flavor of things that is going to come to pass. And then the other thing that we need to know is the type of solvent. Protic solvents, aprotic solvents that are polar, and aprotic solvents that are less polar. THF is sort of in between the two. I view it as a more polar solvent, but it's not as polar as the rest of these. But anyway, so if you've got, so this is where the decision matrix part comes in. If you've got a primary substrate and you look at the Lewis base, the first thing you need to recognize is that it's primary. So is the leaving group, where's the leaving group, and what type of carbon is it attached to? So if it's a primary substrate, then the first question is, well, let's look at the Lewis base. Is it a nucleophile or is it a base? If it's a nucleophile, well, it basically has to be SN2. Is it a base? Well, it has to be E2. If it can be either, so either ones are the ones in the second row here. Let's highlight. These are the either ones. I can't highlight it the way I would like to. Then what we look at is the solvent. Is the solvent protic or is the solvent aprotic? So aprotic solvents favor SN2 reactions. Protic solvents are going to really slow down the rate of an SN2, and it's going to allow the E2 to be favored. So if it's ethoxide or methoxide in methanol, then these are going to be E2 type elimination reactions. If it's, say, the carboxylate anion in DMSO, then this would be an SN2 reaction. That's basically, if it's one of these things in the second row, you look to the solvent and see what it would be. Protic solvents favor E2, aprotic SN2. And it's a similar sort of process for secondary substrates. So if it's a nucleophile, well, it can only be SN2. If it's if it's a base, then it's going to be E2, because the E1 is going to be slow compared to the E2, so the E2 is the one which basically takes control of that. If it can be both, just look at the solvent, SN2, and if it's of a protic solvent, you look at the base strength and it's really weak, then you might get some SN1, but if it's strong, it's all going to be E2. And last but not least, tertiary, if you got a nucleophile, it has to be SN1 because the SN2 is impossible. If it's a strong base, E2. And then weak bases, you might get some SN1. So weak bases would be something along right here, this little part of the chart here. Now, there's actually, I suppose that there's another part to the secondary and tertiary, and that is if the reaction's in E2, is it a bulky base or is it a small base? And then the bulky base will give the least substituted product, and the small would give the more substituted product. But that's, yeah, that would be part of the E2. And it would only be important for the secondary and the tertiary, so that's something to keep in mind. But really the point is recognizing what is what. Checked. Since the E2 can be tertiary. I don't know if I understand this question. So the E2 can take place on any of the three, right? And so we're forming alkene. So in the case, if it's a primary like this, there's only one potential product, and that would be this in the case of primary. In the case of a secondary, if it's not symmetrical, there are two possible E2 products, this one or this one. The least substituted or the more substituted. In the case of a tertiary one, it depends upon the symmetry of the molecule and what the, in this case, there'd be two possible products. One which would be here, and then the other one which would be this, which is the same as this. So E2 can take place on all three. So it's got the most versatility for sure. I don't know if I answered that question properly or not. Um, 15 or 16. Okay, that's basically this. I'll go back to the, this is basically, that's how the decision matrix is supposed to work. And I sent that out in an email. So if you didn't get that yesterday, check your junk mail at for your BU email address if you didn't get it. But this is how this is supposed to work. So only nucleophiles will be this, only bases will be this, strong bases and nucleophiles. If it's in a protic solvent, it's going to be an E2. And in fact, doing SN2 with these types of strong nucleophiles would be risky. Most chemists would use the ones in the second box here as a better. And then the weak nucleophiles would be SN1. Okay, now let's see here. Let's go back to the Okay, so there have been a number of questions about what's going on for the final exam. So we basically are ending with the SN1, SN2, E1, E2. That's where we've gotten to. So on Moodle, there's another part of the alkene section which talks about alkene addition reactions. We're gonna be doing that next term. So that's where we're going next. We haven't gotten to that. So this is where it's basically going to end at this part here. So on Moodle, there was an old exam. I think it's from 2018, which is posted, and it basically ends at exactly the same place where we're at right now. Let's see.